Okay, we have found the TC and the amount of TC, how much this TC is. Okay, then we return to our circuit now, this circuit. Okay, we can then draw, you should draw nicely now. Okay, draw nicely. Means that you can draw either this kind of arrangement. We put all the P rectifier, PD rectifier, PD MOSFET. So the two branches are connected together because we have only one heatsink to cater both device. This is your MOSFET, this is your heatsink connected into single or common heatsink. And MOSFET rectifier connect to one heatsink. So that's why we have here one contains only one R-thermal CS. R-thermal SA heatsink to heatsink, R-thermal SA heatsink into ambient, and heatsink TS here, TC is here, C is here, TS, TA. So you can draw this kind of arrangement or this kind of circuit. So it doesn't matter, depends, both are the same. So what we have to do is that we just publish all the data that which is not available here into the circuit. So we have found our TC just now. So next is to find out what are the contributing TC into PD of our rectifier. Okay, again we have been acknowledged that TJMOS is 100 degrees C. So we have found out the amount of the power that need to be maintained at 4.92 watts, and it produces TC of 86.96. TC and TS are the same because we have R-thermal CS here, which is 0. Sorry, this one, which is 0. So this part is already soldered to the PCB, to the heatsink. So we have 0 thermal resistance. That's why TC and TS, they share the same values of 86.96 degrees C. So from here we shall see what is happening at this TJ rectifier. So the equation will be TJ rectifier is equal to PD rectifier times R-thermal JC of rectifier plus TC. Okay, TJ rectifier we need to find because this is the known already. We have been acknowledged about this TC here, same as TS, 86.96. Okay, 86.96. So we need to find this one is obtained from your rectifier datasheet values information. This one will be based on the values of the current that flows inside our rectifier. Just now 0.6 or 60% through MOSFET. So another 40% will be conduct through your rectifier. So how much you produce your PD here? So PD for dissipated power for MOSFET calculated based on RDS on, and based on our RDS during on state, and thermal from DS during on state. But PD for rectifier will depend on the curve. How much you conduct your current, it produce how much PD directly of your rectifier. So you will find from the curve. So let's see the curve inside our datasheet. Okay, if you open the datasheet, we should see that the body package of our rectifier, it comes with hole. Okay, but when you take a look at your notes, so if you are referring to the previous year's note, so R-thermal CS considered as 0. 0 means that we shall solder the metal tag backplate of your device, into our heatsink. So we shall consider that. So means that this metal tag will be directly intact or soldered to your heatsink. So the thermal RS thermal resistance of your case to heat sink will be 0. Okay, let's see what is the producing heat or dissipated power with our device right now. So we have a few graphs here. Any graph can be considered as information, but for this device, you can see here, maximum the device can conduct up to 8 ampere average. See, I forward AV is your average forward current value. I forward average 8 ampere. Take note on the unit. Sometimes mentioned in average, sometimes in RMS, sometimes in peak. So this one is in average. Average. Okay. So how much PD? So this is your P, power dissipated forward in watts. PF watts. Power forward watts. So this one is defined in duty cycle. Maximum forward dissipation based on how much duty cycle you apply to your switch or to this diode. Okay, at 100% cycle, continuously on. So this is the graph, the curve, and 100%. So means that if you conduct from 2 ampere up to 8 ampere, we can go to 12 ampere. So this one is your curve. But recommended maximum 8 ampere. So how much it will dissipate? So 10, 11, 12, 12 watt. That if you conduct at 8 ampere at continuously on, so it will dissipate 12 watts. If you use 0.5 duty cycle, so at certain values of, let's say, 6 ampere average, so it will emit around 9 watt like that. So this is how to read the graph. So let's say if you use this graph using form factor. Form factor means that IF RMS divided by I forward average. This is form factor. Form factor of maximum 1.57 or form factor of minimum 1.57 or 4 maximum. So this is the curve. So this is the curve. So based on the example, that we have went through inside your notes, how to calculate the average current that go into your rectifier. See, I average rectifier defined by the duty cycle, because 60% went through your MOSFET, so another 40%, 0.4 of the cycle will go through your rectifier. 6 ampere average with 0.4 or 40%, so you will get 2.4 ampere average current average. In terms of form factor, so form factor is defined by IRMS divided by I average, or 1 over duty cycle of your rectifier. So you will get 1.58 in terms of your form factor. So if you refer to your graph again, so 1.58 is around form factor of 1.57. So this is how you want to use, or you shall use your reference inside your datasheet. This is your form factor around 1.57, 1.58. So the nearest curve, this one, with current of 2.4 ampere average. So 2.4 ampere average. So we go into around 3.75 watt of dissipated forward power. Means that the device will dissipate. It has loss of 3.75 watt and 3.75 watt. So this is your PD that you shall use inside your calculation. This one. Okay. So your PD is 3.57 watt times your R thermal JC. How much? R thermal JC from your datasheet. R thermal JC JC. See, R thermal from junction to mounting base. R thermal junction this case, so the same, is 2.0 and 2.0. So times 2.0 plus TC of what we have calculated just now, 86.96. So you shall get your TG rectifier of how much? Okay, 3.75, bukan 57, sorry. So you get your values of TG rectifier of 94.46 degrees C. So this is your TG rectifier of 94.46 degrees C. And TG rectifier. Okay, so done for the calculation. So you just furbish your circuit with all the values here. Okay, done for your rectifier and MOSFET part. But now we want to check. Is this heatsink sufficient or not to cater the losses that occur inside our MOSFET and rectifier. So means that we want to check how much actually the required heatsink, because we are provided with 3 degrees C per watt of heatsink. So does it sufficient or not? Does it sufficient or not? So how to use or to calculate the values? So we take the another point of TC or TS here, and TC and TS we have the same value here, so we put it as TS, and TS equal to PD total that occur from your MOSFET, come from your MOSFET, and also share with your rectifier. So it will flow to your ambient. So with this arrow, so this is the formula or the equation, equilibrium equation happen here. So with the PD total, it comes from MOSFET, and rectifier, and PD total is equal to thermal SA plus TA. So this is the unknown that we want to find, and you can check using the available heatsink to see how much actually the TS, or we shall check how much heatsink size that we require. So TS now we have 86.96 degrees C. PD total is 4.92 plus 3.75. Just now we calculate. Thermal SA that we need is the unknown for this time. Thermal SA. T ambient is 50, and 50 T ambient. Is it? Okay, 50. T ambient is 50. So you calculate accordingly. You try to find out how much is your required thermal SA. How much is that? Thermal SA. So how much you get for thermal SA? So the final value you shall see, or you shall find as 4.26 degrees C per watt. So this is your required values of thermal SA. The size of heatsink that you require or you need for the system to keep down or cool down your rectifier junction temperature and your MOSFET junction temperature to that level is this size of heatsink, 4.26 degrees C per watt. So now you are being provided with 3 degrees C per watt of heatsink size. So the question is that thermal management determine operational power is when the provided heatsink is 3 degrees C per watt. So means that does it sufficient or not to determine or to maintain the MOSFET and your rectifier in operation with this kind of required heatsink, provided heatsink of 3 degrees C per watt. So you compare these two. So which one is better? And for sure 3 degrees